Everyone, so today we're gonna discuss something very basic. Whenever we use this Laplace transform, we use the S, right? The S domain. So today we're gonna discuss that what is this S? What does this actually mean? Before I proceed, I would like to have a little bit discussion of what is a frequency domain, right? Because we keep hearing this thing that we used to work with frequency domain instead of the time domain in the control systems. It's like, to be very quick, the frequency domain, we had first of all the Fourier series, right? So in Fourier series, what we could do, if we had a periodic signal, we can split it into multiple components, right? So we had this first technique, Fourier series, but after some time we realized that not all the signals that we deal with are the periodic signals, right? So a lot of them are non-periodic. So to deal with the non-periodic signals, what we came up with is Fourier transform, right? So with the Fourier transform, we could deal with the non-periodic signals, right? We can see through the Fourier transform that what is that particular non-periodic signal composed of. So when we have these type of two techniques, then why we have the Laplace transforms? The need for Laplace transforms came because we wanted to know something else, right? So let's say we have a signal. We had a square wave, something like this. So we do Fourier transform, and we see that okay, this is made up of this signal and a lot of other signals. So this is what your Fourier transform does. It tells you that what is the composition or what is the different frequencies involved in that particular signal. So we were not only interested in the frequencies, but we also wanted to know that whether those frequencies behave like this or they go like this or they go like this. So what is this? This is frequency plus its amplitude. So with the Fourier transforms, we could only know that what are the frequency components of that specific signal, right? But we didn't know what is the amplitude of that frequency signal inside that specific signal that we have been given, right? Does this expand? Does that decay out, or does that keep its amplitude constant, and things like that, right? So what we have right now to do that, we have Laplace transform. We have a Laplace transform for that, right? So in the Laplace transform, we use S domain. Right. We have the S domain. Now what is S? This S is actually sigma plus j omega. What is the omega? This is the frequency. This is the frequency. Like, what is the frequency of that specific signal? This is the decay or expansion of that specific signal, right? So the decay or exponential is denoted by this e power minus t. This is the decay, or e power plus t if the signal increases, right? If we look at the graph, e power minus t is like this, and e power plus t is like that. So when this thing is merged with this imaginary part or the frequency information, what we come up with? We come up with a signal which behaves either like this or it behaves like this. So now you can easily see that what is the advantage of having such signal, right? In the control systems, we keep dealing with these signals, and so that we could know that how the signal behaves over the time. Does it will it remain stable or it will go unstable in the time? So how this S is actually telling us this information, let's have a very quick example. So let's start with the very simple signal. It's used a lot in the control engineering. It's called the step signal. So step signal looks something like this. If this is t, this is the amplitude. It's just like starts at some time and continues like that, right? So let's say this is t is equal to 1, and the step signal is like starts at 1, then it stays like that. Laplace of, let's say, f of t will be f of s, right? In this case it will be just or this f of s, I'll just complete it. Start from 0 to infinity, e power minus st f of t dt. So this is how we find out the Laplace transform of a particular function, which is f of t. It's given in the time domain. The Laplace transform of the step signal 1 would be like this: 0 to infinity, e power minus st and dt. If you do the integration of e power minus st, it will be minus 1 over s e power minus st, and these are our limits within which we have to do the integration. So to solve the limits, we know how to do that. We do the upper minus lower, and we put these limits inside this t, the variable which we are doing the integration with respect to. And here we have 1 over s e power minus s infinity minus, and again minus 1 over s e power minus s 0. In this case, we will assume that our s here is greater than 0, right? So why we do this assumption? Because we want this negative to stay negative. If the s is positive, this negative and negative will be multiplied, and the infinity will be positive. So if s is less than 0, what will happen? E will be having a plus infinity, which is something like this, right? So it doesn't converge to any value. So what happens? It stays at infinity. We don't need that, right? So when the s is greater than 0, what happens? This will be this e power minus infinity, and this will be minus and minus plus, and it will be 1 over s e power minus 0, and whatever it is e power will be 0. So what would you see in here is that e power minus infinity, this will be something like this, right? So infinity means like it will converge to some value very small, and that is 0, right? So what we can say in here, this will be 0, and this will be 1 over s e power 0 is 1, and which is 1 over s. So the Laplace of a step is 1 over s, right? What I can do in here is that the roots or poles of 1 over s is like, what's the s? S is equal to 0, right? S is equal to 0. So this means that the sigma and j omega both are 0. So what we basically find out in here is that we don't have any decay or any expansion. It's just e raised to power 0, and we have 0 and j. So no frequency, and we just have this value of 1, and we have no frequency, which we actually can notice that we just did the Laplace transform of a step signal, and it's just a specific value and it has no frequency. So this is the intuitive information that we get from this as variable. Another signal that I want to discuss is this one. F of t is equal to e power at, right? So we want to find out the Laplace transform of this one. So Laplace transform of f of t, we know it becomes f of s, which is 0 to infinity e raised to power minus st, ft, and dt. Okay, so Laplace transform of e at is equal to 0 to infinity e power minus st and e power at dt, right? And as we proceed, 1 over a minus s e raised to power a minus s t, and the limits like this, right? So as we have to input this these limits into this t, so we can take this out, and we are left with a minus s t infinity and 0. We again have kind of a same problem. We want this t, right, this factor to be negative when you put the infinity over here. So let me do that first to be very to be more clear. This actually is this a minus s upper limit minus this minus c lower limit, so a minus s and the lower limit, which is 0. Okay, so what we need, we want this part to be negative, right? Because if this is positive, e raised to power plus infinity will just explode and it will not convert any value. But if this part is negative, a minus s is less than 0, what happens? E will be having negative infinity, which will be equal to 0, right? So a minus s less than 0, which means that a should be less than s, or s should be greater than a, right? So we assume this part, and when we assume this thing, what we are left with is this 0, which actually means that we have 1 over a minus s minus 1, right? Or so actually what we got is this f of s, which is, what was f of s? It is the Laplace transform of e raised to the power t, and this one. So now we just try to understand that what this simple polynomial tells us. Okay, so here we can see that what are the poles of this specific thing is that S is equal to A, right? So we have a real pole, we have a positive pole. So in control engineering, positive pole means that the system is unstable. So why it's unstable? It says that it's equal to A, which means that we have sigma and we have j omega, right? So we have only sigma, we don't have any omega, right? So the frequency component of the signal is 0, and the way it expands or decays is the A, right? So we know that we denote this expansion or the decaying of a signal with E, and this is happening at the rate A. So, and this is positive, so we can see that it will always go like that, right, up to whatever value we have. So it's not going to converge to any point. So this is another simple signal or a simple function, and here we have its Laplace transform, and here is what we can say that we actually see from this specific polynomial, right, which is simply the S. And likewise, if we wanna do the Laplace transform of a raised to power minus at, like, which kind of converges to some value and graph looks like this, you will see that the Laplace transform of e to the power minus at is equal to 1 over s plus a, right? So 1 over s plus a means that we have pole like this, right? And if we just write it in g omega thing, this is a sigma, this is the j omega, which is equal to 0. So this sigma tells us that we have the E, which kind of decays with rate A, and the signal has some decaying, some converging properties, and it will converge to some point, and has, we can say that this system is stable because it kind of converges to some specific value and doesn't explode if we progress in the time. And one last signal that I want to discuss, it's also very interesting. This would be something like this, and this will be multiplied by some sine signal, right? So we can see that this sine signal will eventually decay out like this. Okay, so let's do the Laplace transform of this f of t and see what we have, right? So if we'll take the Laplace transform of this, you will come up with 1 over s squared plus 2s plus 2, right? So this is the Laplace transform of this signal. Now if we take the roots, or if we have a look at the poles of this polynomial, which is x squared plus 2s plus 2, the poles would be s1, because this is a quadratic equation, it will have 2 poles, and you will have to use the quadratic formula to solve this equation. So when you do that, you will see that it is minus 1 plus j, and the other pole would be s2, and that will be minus 1 minus j, right? So if we just take the s1 pole, minus 1 and plus j, we can see that this is our sigma and this is our j omega, right? So it tells us that we have some signal which decays with the rate of minus 1 in the time t, and it has some frequency, right? It has some frequency which as omega is 1, because there is no value, we say that it is 1 radian per second. We can do this intuitively, that okay, this equation represents some system which has this exponentially decaying response and has some frequency factor involved in it. So I hope this s variable would make a little bit more sense than we had before, right? This is not as a mystery as of now, that what this s is. This makes these time domain calculations, simple. When in Laplace transform, they simply become the algebraic. So we can deal with these equations like we used to solve this the simple algebra, and it solves a lot of things in one go, right? All we need to do is like convert all the complex things in the time domain into the frequency domain, solve the things, and then just take the inverse Laplace of it to get back the response in the time. So let's open the Simulink and see some of the examples in here that we already did right now, right? I have already made these models, and I'll just simulate it and discuss what we have inside. First of all, I'll be discussing e raised to the power minus exponential of minus t, and we just did the Laplace transform, and it came out to be 1 over s plus 1. So here, if you double click, you can see that we have some signal like this, but we also know that the signal e raised to the power minus t doesn't look like it, right? It's increasing over here, right? What it should look like is this, right? So I have this function defined over here with y equal to e exponential of minus t, right? When you simulate it, it should look something like this, right? But when we simulate the Laplace transform of the same function, which is 1 over s plus 1, we get some signal like this. So why is that? The answer is because the way the Matlab simulates this transfer function is it uses this step signal, right? So this step signal, which is 1 over s, we did that as our first problem in this video, right? So what happens, this 1 over s gets multiplied by this transfer function, right? And like this, we have a step, and we have a step, and we have a transfer function s plus 1, and the resulting thing would be, if this is 1 over s, this will be 1 over s squared plus s. So and the actual thing that Matlab simulates is this with respect to time. Okay, so what happens when you take an inverse Laplace of this thing, you will see that it is equal to 1 minus exponent of minus t, right? So what we do when we in the time domain, if we simulate this equation, 1 minus exponent of minus t, we can have the same result as we have in this transfer function. So if the transfer function looks like this, goes to 1, and in this function block I have 1 minus exponential of minus t, and if I see the result, it's the same, right? So when the Matlab simulates it, it becomes a little bit different because we are using this step signal, right? It's not just the simulation of this the function of which this specific transfer function is. And if we go to the positive exponent, we also know that we have the Laplace transform of e raised to the power plus t equal to 1 over s minus 1. It expands over the time, right? So given the simulation time, which was 10 seconds, it just goes up to 10 raised to power 4. Otherwise it can go up to the infinity. So here, so as that goes to the infinity, so whatever you simulated in here, like y of exponent of t and the y of exponent of t minus 1. So the way in this block diagram is simulated because of the step signal would be 1 over s squared minus s. So when you take inverse Laplace of 1 over s squared minus s, you will see that it is exponent of t minus 1, right? So but this goes to the infinity, so what happens that all the three graphs are more like same. And this is a very interesting signal, and it is like this. And if you remember, this is actually the Laplace transform of e raised to the power minus t multiplied by sine of t. So when we do this step signal, it looks like this, right? It's also very different because we don't see any sine wave or anything else over here. Also doesn't go to the 0, right? It just stays at 0.5. So what we expect, right, this simulation, because of the f of t, which is for which this transform we have been given, right, we kind of expect something like this, right? We have this sine which decays over the time, and this is how you simulate this equation: exponent of t sine 2 pi, because this is accepts in the radians. So I have converted into the radians. When you actually find the response of this equation, you will get this, right? But same equation of which this is the Laplace transform, when it is simulated with the step signal, it is like this. So why is it that different? So again, this is because of this step signal. So when this step signal is multiplied with this block like this, so we have s squared to s plus 2, and this actually becomes 1 over s cubed plus 2s squared plus 2s, right? So now if you take the inverse Laplace of this thing, it becomes something like this. E raised to power t at minus underscore 2 sine t plus pi upon 4, like this. So just by adding this s, we can see that our Laplace transform has changed drastically. So I'll take this opportunity to mention this advantage of this Laplace transform, that when this signal is represented in the Laplace transform, it just is simply the multiplication like this, right? But in the time domain, it's a quite complex looking signal, and this signal has the information of the step, right? The step embedded. So that's a big thing, right? And so how the way the Laplace transforms make the complex looking signals very easy, like in this form, right? So if you take the Laplace transform of this, you will end up getting this equation. If you take the inverse Laplace of this, you will end up getting this equation, right? So let's go back to the Simulink and try to simulate. So I have written this equation over here, and if we simulate it, it will be something like this. So you see, it's the same signal as we would get in this Laplace transforms.